So as we discussed, so this neutral point voltage, so this is one of the drawback of this diode clamped multi-level inverters, right? So this is because, so here, so there is no switching redundancy. So we created some switching redundancy by using the space vector modulation, right? So it is balanced the capacitors to a large extent. It is balanced the capacitor to a large extent. But the thing is that, so when you go for higher levels, more than 3 level, 4 level, 5 level case, right? So this problem cannot be solved completely. So therefore, so what we have to use is, so we need to look for alternative methods. So we need to look for alternative methods. So one of the alternative method is using external circuit to balance the capacitors. Using external circuit to balance the capacitors. Right. So how exactly it will be? So this is the capacitors, right? For example, we are using this for some other applications, like, so when this problem is actually arise, so when we are using this or when you are connecting this to a grid, so then this problem will arise. Okay. So thing is that, so let us assume that this inverter is used for an application like active rectifier or active front-end converter, or if it is used for an applications like DCMLI. So used for some applications like DCMLI. Right. So now the thing is that, so if you are using for a DCMLI, so it will now, so you must charge these capacitors with the appropriate voltages, and we have to make sure that these two capacitor voltage must be balanced. Okay. So these two capacitor voltage must be balanced. So here the thing is that this is a very difficult task. So when you are implementing this, right? So here, if you are aware that if your two capacitors are there, you remember that, so we normally use PI controller. So if a single capacitor is there, so this will be your VDC reference, okay, and this will be your VDC actual. So if it is a single capacitor, okay, thing is, now we need to process this in a PI controller, for example, and this will gives you the required amount. So right, so the required amount of power, right, or required amount of current, so that requires to drawn by the grid, so that the T capacitor or this, so that the actual capacitor voltage will balance the or to follow the reference voltage. So this is how we will implement, right? If you remember that when you study the active rectifiers, so this is how we implemented. So the actual voltage is compared with the reference. Okay. So this error is processed in a PI controller. Job of the PI control is to, so make the steady state error between these two 0. So it will make the steady state error 0 means, so this actual one is follows the reference one, right? So this is if you have only one capacitor. Right? So what exactly we have to do for two capacitors, right? So in the same thing, so if you have this VD reference here, so this is the VD actual. So that means you measured this voltage, the sum of the two capacitor voltage. So this will be the VD actual, and you are connected to a PI controller. Okay. So now the thing is, for example, this is 400 volts. If it is assumed that this is 400 volts. So when you're implementing this one, right? So if you assume that you have properly tuned that, so here the sum obviously you will get, so this voltage you will get 400 volts. So if you have properly tuned the PI controller, and if it is properly working, so you will get 400 volts here. But the thing is that, so you're not sure, so whether these two are giving 200 or 200. So you will not sure whether these two are giving 200 volts or 200 volts. Right. So how to ensure that, so whether these two will be 200 and 200, right? So that means if it is two capacitors, the thing is, there is slight change in this one. So how exactly it will be? So let us assume that, so VC1 and VC2 are the capacitor voltages. So this is the sum of the two capacitors, so VC1 and VC2. So this will reference to VD reference, right? So this is plus here, minus here. So this is processed in one PI controller, and this is giving some output, some controlled variable. So it will give, right. So that means this ensures the sum of these two capacitors, so which is equal to VD reference. Okay. So but it will not guarantee that, right? So it will not guarantee that. So these two must be same. So therefore what we can do is, so we have additional PI controller. So where we have difference of this one, VC1 minus VC2, right? So now tell me, so what we need to equate this? So what we need to equate this? So what is the reference here? Hmm? What is the reference? So what it's supposed to be? Yes. The sum we are equated to VD reference. So what should be its difference? So if you have balance of these two voltages, so it is obviously 0, right? Okay. So it is obviously 0. The sum should be equal to the VDC reference, the total DC link voltage, and the difference must be equal to 0, so that if you are doing so, so you will get VC1 must be equal to VC2 ideally. Understood? So whenever you encounter two capacitors, if you want to balance that, so one of the simplest way is to sum must be equal to VD reference and the difference must be equal to 0. So that ensures so VC1 equal to VC2. Right. So here these two control inputs, so we need to add together. So this will be the overall output of the PI controller. This will be the overall output of the PI controller. So this is how we will tightly balance the capacitor voltages, right? So even though you are doing this, right? So you not ensure that, so it may not balance this PI controllers, right? So it will not ensure the proper balance of this. So therefore, so what we have to do is, so we need to use some external circuits. So this is one of the simplest way, right? By using two PI controllers. So that will almost gives you the accurate results, right? So if you want further accuracy, so we have some external methods. What we have to do is, so we need to use additional circuits. The additional circuit, it will be something like this. So that is its upper switch and it will be the lower switch. All right. So this will be the upper switch and it will be the lower switch. Right. So here, normal operation, right? Under normal operation, right? So this SL and this additional circuits, so there is no job for this additional circuit or this auxiliary circuit. Okay. So here, if you observe that, so what exactly it look like? So this is the DC, right? And we are modulating that DC. So what exactly it look like? You might have studied, right? 4-quadrant chopper, 2-quadrant chopper, say, and single quadrant chopper. So what exactly this is? 4-quadrant chopper, 2-quadrant chopper, or single quadrant chopper? So what is this circuit? It is a 4-quadrant chopper, 2-quadrant chopper, or single quadrant chopper. Of course, it's definitely not a single quadrant, right? So we have 2-quadrant or 4-quadrant. Hmm? Will it be single quadrant or 4 quadrant? So 2 quadrant or 4 quadrant?
4, sir.
4 quadrant. So how many switches for a 4 quadrant chopper will be there?
Switches.
How many switches for a 4 quadrant will be there?
4 switches.
4 switches, right? So 4 quadrant means you must have 4 switches, so that so you have forward motoring, forward regeneration, reverse motoring, and reverse regeneration. So that occurs. So here this will be only 2 quadrant. Okay, if you have 2 switches and the split capacitor, so that will be a 2 quadrant, right? So instead of that, if the switches are present here, so switches are present here, and we have DC source outside, right? So that will be your 4 quadrant. So that is similar to your H bridge. Cascade H bridge is there, right? So H bridge and 4 quadrant chopper both are same only. Thing is that the operation is different. Remember that. So H bridge, full bridge, and the 4 quadrant choppers, so both are same. Circuit wise, both are same. But the firing pulse, so how we are controlling the firing pulse, so that matters. Okay. So in inverter, all the 4 switches are operated together. So whereas in chopper, so only 2 switches are operated. Okay. So only 2 switches are operated, or only 2 switches are modulated. Right. So this entire thing forms a 4 quadrant chopper. Okay, so the main advantage of main operation of the 4 quadrant chopper is if you have 2 circuits are there, so energy stored in one circuit is transferred to the other circuit and vice versa, right? So why exactly we use this? Let us assume that so our target is to balance these 2 capacitors to 200 volts, right? So this must be 200 and this must be 200, right? Somehow, right? So let us assume that so this voltage is 210 and this is 190 volts. Okay. So now, so what will happen if this is 200 volts, right? So this will be 200 volts. So 210 volts. So now what we have to do is it is supposed to be, so this voltage is supposed to be reduced. Okay? So this voltage is supposed to be reduced and this voltage is supposed to be increased. So we need to increase this voltage, right? So that means energy stored in this capacitor, so it is of CV square. Okay, and this is also of CV square. So the energy stored in this capacitor so will be high when compared to the energy stored in this capacitor. Right. So but ideally the energy stored in these 2 capacitors must be same. So that is what we require, right? So now the thing is that so we have some additional energy in this capacitor. Somehow we need to transfer this additional energy to this bottom capacitor. Somehow we need to transfer this additional energy that's stored in the capacitor to the bottom capacitor, right? So how exactly it will can be done is that so whenever so we have identified it's supposed to be 200 and this is 210, right? So when you observe that, so what we have to do is so we need to close this switch, or we need to give the firing pulses to this switch. All right. So now what will happen? So now what will happen? So here, right? So now it will formulate a current. It will flow like this, right? Agree? Agree? So if you assume that this inductor is initially uncharged, okay, so this energy is transferred to this inductor. The energy is transferred to inductor, right? Understood? So now the capacitor is slightly discharging and the inductor is slightly charging. Understood? So the capacitor is slightly discharging and the inductor is gaining some energy, right? So how long you need to turn on this switch? How long you need to turn on this switch? How long you need to turn on the switch? Until this is now this voltage is 210 volts, right? Okay. So now this voltage is 210 volts and the switch is on. So the energy is dissipating. So obviously the energy is dissipating or energy is transferred to this inductor. So that means this capacitor voltage is reducing. So now it is reduced to 209, 208, 206, 205 and 200. So as and when it reaches 200, so this is the required voltage. This is the required voltage, right? So this is our required voltage. So as and when it required reaches 200, so now you need to open the switch. Okay. So if you are continuously on, so thing is that, so now voltage will be reduced. Now it will be 199, 198. So this is thing what we don't require. So we need to maintain this 200 voltage. Okay. Thing is that, so as and when it require, or as and when it reaches 200 volts, so we need to open this switch. Okay. So we need to open this switch. Understood? Right. So if you observe that the upper capacitor voltage is greater than the reference, so you need to turn on this additional switch SU. Right. So how much duration you need to turn on until the capacitor voltage reaches to its reference value 200 in this particular case. Right. So now this excess energy is stored in the inductor. So now this excess energy is stored in the inductor. Right. Agree? So excess energy, so which is equal to the 10 voltage dissipation or 10 voltage decrease in the inductor or capacitor voltage. So now it is stored in the inductor, and this is the current direction. Understood? So now this will be the current direction. Right. So now what we have to do is this additional energy, so we need to transfer to this capacitor. So whatever this additional or whatever the energy stored in this inductor, so we need to transfer this capacitor. So how exactly will transfer? So what we have to do now? So what we have to do? So how to transfer this? This is the current direction, right? So how to transfer that?
Diode.
Okay. So how exactly it will transfer? So if you observe that, if you turn on this lower switch, okay. So if you turn on this lower switch, okay. So now the thing is that the current is moving in this direction, right? So the inductor will not allow sudden change, or inductor will not change this direction, right? So now it will move to, or it will formulate a circle here. Understood? So now this switch will be closed and this diode will become forward bias. So therefore, this circuit, whatever the energy stored in this one, so that is transferred to this capacitor. So now the capacitor will slightly increase, right? So the capacitor voltage will regain and it will reach 200. As and when it reaches 200, so now what will happen? If it is reaches 200, so this diode will be reverse biased, or this diode will, or otherwise, so we need to turn off this switch. So we need to turn off this switch. Okay, understood? So this is how the transfer of the first capacitor, the top capacitor, is reaches to the bottom capacitor. Similarly, right? Similarly, if this capacitor voltage is 210 volts and this is 200 volts, okay, so this is 200 volts. All right. So this is the excess capacitor. So that means this is transferred like this. With excess voltage, that is transferred like this, and this one, so this is given to, or this is feed via this this diode. All right. So this is, so how exactly, by using a 2-quadrant chopper, so energy stored in the upper capacitor is transferred to lower one, and vice versa. So because, and we are using this inductor as medium, so first it is transferred to this inductor and it is transferred back to capacitor. So we need to turn on so appropriate switches, right? So we need to turn on the appropriate switches to obtain the balance among the two capacitors. Understood? You have any questions? You have any questions?
Sir,
Yes.
this capacitor imbalance occur only during small vectors only, sir.
No, not during small vectors. Only small vectors are causing the capacitor voltages.
Ah, imbalance. That imbalance during
Yeah.
small vectors. But this circuit work irrespective of the small vectors and medium vectors.
So this is general circuit, okay, irrespective of the PWM technique. So this circuit works, okay. So we have dedicated circuit to balance the capacitors. Right. So now what we have to do is, so we need to design the, or we need to generate the firing pulses, right? So we need to, so additional to along with this, okay. So for control of this one, either we can use SVM or else you can use level shifted PWM. So any of the PWM technique, so we can use here. But to control this S upper and S lower, so we need to implement one algorithm, right? So we need to implement one algorithm. So how exactly that algorithm is? Something like this, right? So first thing is, so we need to compare. So we need to compare this capacitor voltages. So let us assume that, so this capacitor voltage is VC1 and this is VC2. So can anyone tell, so these two SU and SL are complementary to each other every time? So this SU and SL, so is these two are complementary?
Sir, otherwise short circuit only.
If these two are complementary, right, so it is not necessary to be complementary, right? It is not necessarily to complementary. So there are some cases, right? So for example, this is 190 volts and this is 180 volts. Okay. So in this case, so which switch is on? So which switch is on?
SL.
Why SL?
Upper switch.
Upper
We are
switch.
supposed to maintain 200 volts.
Okay.
Both are different.
Hmm?
Both are having less voltage.
So you're supposed to maintain 200 volts. Let us assume there is one scenario. So where you have 190 volts and 180 volts. Okay. So which switch is supposed to on? So if you observe that, okay, so if you notice that, so whenever this capacitor is excess charged, so then only we transfer the energy to the bottom one, right? So for example, in this case, if you turn on this upper switch, right? So if you turn on this upper switch, the energy stored in this one is transferred to here. Okay. But these two, when you're doing so, somehow, so this is 190 volts and this is 180 volts. Maybe they both are set it at 185 volts and they both will set it at 185 volts, right? Agree?
Yes. Yes.
Right. But the thing is that you're supposed to maintain 200 volts. So what we have to do is, so this must be this energy, the energy that requires to 200 volts. So that must be drawn from the grid. Okay. So that energy must be drawn from the grid. So this setup will not give the excess energy, right? As this setup will not give the additional energy. The thing is that, so it is upper capacitor is overcharged, it is transferred to bottom one. If it is bottom one is overcharged, that is transferred to upper one, right? But they will not, right? But they will not maintain this 200 volts, right? So whenever if you want to maintain this one, so we need to balance this one, right? So that's why we have this outer PI controller, or this PI controller. The job of this PI controller is to make sure that, so that is equal to 200 volts, 200 volts. Okay. So now the PI controller will play a role. So when this is the case, right? So when it's less than the reference value, so there is no job of this additional circuit. In that case, it must be drawn from the grid, right? The capacitor must be drawn from the grid. So let us assume that, so what we have to do is, first thing is we need to compare VC1, that is the first capacitor voltage, with V reference. Okay. So VC1, so we need to compare this V reference. So if VC1 is greater than V reference, agree? If VC1 is greater than V reference, so we need to turn on. So we need to turn on, right? So we need to turn on S upper. Is this only one that is sufficient? Is it the only one? So that is sufficient. Right. So we need to compare the second one also, right? So that is VC1 and VC2. So there is a chance that, so let us assume this is 210 volts and this is 210 volts. So this is 220 volts and 210 volts. Right? So now which switch you will on? So now which switch we will on? So which switch you will turn on? SU will turn on or SL you will turn on?
We might connect that to some discharge circuit.
Mhm.
sir. We need to connect to some discharge circuit to maintain 200 volts.
So what we have to do is, the first thing is, this is some special cases, right? 180 less than the reference value and greater than the reference values. It is usually occur at the beginning, right? So in this case, it is 220 volts, right? Thing is that this is 210 volts. So here we already discussed that there are two controllers. We have another PI controller, so that are working. The PI controllers are continuously working to maintain this reference voltage 400 and individual capacitor voltage to 200 volts, 200 volts. So this is compulsory. Okay. So this is compulsory. So in addition to that, to reduce the burden or to reduce the burden on this PI controller, so we have this additional circuit. So we have this additional circuit to reduce the burden on this PI controller, right? So here what this circuit will do, this is 200 volts, right? This is charging excessively. So therefore what exactly in the same time, so when the PI controller is trying to maintain 200 volts, 200 volts, at the same time this excess charging is so immediately is transferred to this bottom capacitors. Okay. So this excess charge is immediately, or this excess voltage in this one is immediately transferred to this bottom one. Right. So therefore, it is trying to reduce the gap between the voltages. That will trying to reduce the gap between these two voltages. Understood? So if this is the case, somehow they will settle somewhere around 215 volts and 215 volts. So now the job of this PI control, it will be easy, right? The job of PI control is easy. Why? Because in PI control we have some of the two capacitor voltage, so we are equating to V reference, and the difference we are equating to 0. So now this difference is it is making it 0, right? So that means one PI controller output will be, then one PI controller, the one PI controller of error is regulated. Okay, so the steady state error of one PI controller is naturally becomes 0 with this additional circuit. So what we have to do is, so we need to take an action, so which capacitor voltage is high. So in this case, we need to see this VC1 and VC2. This is the case, all right? So this is, let us assume this is 220 volts and this is 210 volts. Okay. And this is 200 volts and this is 220 volts. So what is the output of this one? So what is the output of this? What is the output here? 1 or 0?
1.
It will be 1, right? So what is the output of this? So what is the output of this? Which is high, VC1, VC2? What is the output? You will get 1 or 0 here?
1.
1 only, right? Okay. So now based on these two, so we need to identify the switches, right? Similarly, so we have another one. So before completing this, so now we have VC2 here, V reference. So this is for bottom signal. So this is VC2, VC1. So now we already discussed this is 210 volts. So this is 200 volts and this is 210. This is 220 volts, right? So now what is the value here? So what is the value of VC2? What is the value of this VC1, VC2? It will be 1, right? Agree? So what is the value here?
0.
0, right? So now tell me, so what is the appropriate switch we need to turn on? So what is the appropriate switch? So we need to turn on upper switch or lower switch. So what is the one we need to turn on? So how to match so these conditions? So how to match so these conditions, right? So if we assume that if this is not there, okay, right? So in this case, so VC1 is greater than V reference, so VC2 is greater than V reference, right? So that means this is also 1, so that is also 1. If both are on, so that will cause short circuit. Agree? So that will cause short circuit, right? The thing that is if we include this additional constraint to prevent short circuit, so this is VC1 and VC2 are on, so this output is 1, right? But actual practice, we are supposed to turn on the upper switch, right? So from our theory, what you understand that, so you're supposed to understand the, you're supposed to turn on the SU. So what we have to do is, we need to multiply these two. So if we multiply these two, what you will get here? 1. So that means you need to turn on SU. Similarly, we need to multiply these two. So that will gives you S lower. Okay. So why exactly we are multiplying this? So because to prevent the both turning on and turning off. Okay. In some cases at the beginning, so there is chance that so both will turn on and turn off. Right. So let us assume that so there is another one case. So we have 190 volts here. So reference is 200 volts. And this is 190 volts. So 190 volts and this is 180 volts. So this is 180 volts and this is 200 volts and 180 volts and this is 190 volts.
180.
So now tell me, so which switch is on? So which one is supposed to on? So this is the case, right? So what this output is 0 and this output is 1. Okay. So VC1 is greater than VC2, but but VC1 is less than the V reference. In this case, we are not supposed to turn on the upper switch, right? We are not supposed to turn on the upper switch. So that's why if you multiply these two, so you will get 0 here. So similarly, it is 180 volts. So this is you are getting 0 here, and this is also 0. So that means this output is 0. So both switches are off. So this is one case, right? So now there is another case. So where VC2 is high. So this is 190 volts and this is 200 volts. So this is 190 volts and this is 210 volts. So we have different options will be there, right? So if you have VC1 is there, VC2 is there, VC2 is there. So these two, so we have some relation is there. VC1 may be greater than VC2, VC1 may be equal to VC2 or VC2 greater than VC2. So these kind of relations, we are doing this several possibilities. So this is VC2, this is 210 volts and this is 200 volts. And this VC2 is again 210 volts and this is 190 volts. So now tell me which switch is on in this case. So this is 180 So this is 180 and 180, right? This is 0, so this is also 0, and this is 1, so this is 1. So therefore, the lower switch is on. Understood? Understood. So this is how exactly we will control the upper and lower switches. So when one of the capacitor voltage or both capacitor voltages are crossing the V reference point. Okay. So we'll stop here. So you have any doubts? Anyway, we will